Hello and welcome, class, to part 3 of chapter 17, wherein we will be building off of our previous lecture, only instead of focusing on the pH scale and the solvent's importance when it comes to the nature of acids and bases, we are here going to be talking about the inherent strength of things that we label as acids and bases once they come together and begin to interact. As a reminder, in part 2, we did learn that an acid can only be an acid, or at least exhibit acidic properties, when in the presence of something that can act as a base. And similarly, bases can only act as bases when in the presence of an acid. However, not all acids are the same, and not all bases are the same. So today we're going to be learning about what molecularly causes different strengths of acids and bases. So what sets weak acids and weak bases apart from strong acids and strong bases is that they partially dissociate in solution. So a weak acid, and we're going to talk about this case of A, weak acids partially dissociate in solution. So these are going to be species that react with water reversibly. This can be generically represented by this equation represented below, where we have some weak acid, actually I'll just do this, weak acid, HA, being dissolved into water, which is a liquid in form. What again sets apart aqueous from liquid is that aqueous implies that something, whatever the species is dissolved in water. So the water cannot be dissolved in itself, hence why the phase here is a liquid. But when HA comes into contact with water, it is going to break into a minus, and the H plus is going to move over to the H2O. So that's going to give us an H3O plus concentrate, or H3O plus in aqueous solution. Now, since this reaction is reversible, because again, this is a weak acid that we are looking at, we can write some type of equilibrium expression. To represent the balance of products to reactants in this solution. The new special Kc that we're going to be working with is known as a Ka. This is the equilibrium constant that is going to be the expression for a weak acid in solution. So much like the KSP or the KW case, there's no special math, it's just a simple label change. Ka now is going to represent the equilibrium constant expression for a weak acid in solution. And we can see that we are taking the products here, the A minus and the H3O plus, they are in the numerator as they have been for any equilibrium expression, and our weak acid is the only reactant that we are including in the denominator, since it is the only reactant that is in the aqueous phase. So we can use this equilibrium expression to perform any of the calculations that we would want to do surrounding some type of weak acid as it exists in solution. We are not going to forget, though, the concept of pH that we introduced on Monday, and that oftentimes our concentration of H3O plus is going to be measured at equilibrium through some type of pH measurement. And we can use that to our advantage when it comes to filling out our ice table or filling out, the equilibrium table, however you've been referring to it, which will give us information about the solution as it exists physically sitting in some type of beaker in front of us. All right, well, with our definition of Ka and the reversibility of weak acids, let's talk about what makes then acids strong. Like what makes larger Ka values, or what even makes a strong acid. A strong acid is defined as being stronger than the conjugate acid of the solvent, which in our case is going to be H3O plus. So any acid that is stronger or dissolves more freely than H3O plus is going to be defined as a strong acid. And these strong acids, again, were on that table of strong acids. If water is our solvent, we are talking about HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. Specifically, the first hydrogen that comes off of H2SO4 is going to be a strong acid. So each of these 7 acids dissociates H plus, or donates H plus to solution more strongly than what H3O plus is able to reversibly react. So in the, let's say, hypothetical reaction of HCl plus H2O goes to H3O plus and Cl minus, this reaction, this donation of H plus from the HCl to the H2O is so strong that there is no reversible reaction. H3O plus is so weak compared to the very, very strong acidic property of this HCl that none of this H plus is going to be donated back to the Cl minus. This is going to be a complete reaction. All right, and then of course, any acid that's not on this list of 7 that would count as a weak acid is going to have a little bit of a reversibility to it because the H3O plus would be able to donate this H plus back to the conjugate base. So our question is, what makes this gradient? Like, what makes these 7 acids so strong versus what makes some other acids so weak? Well, it basically comes down to the structure of the acid. Like if we're keeping our solvent constant, which is water, so we know that that's going to be a controlled variable, the only other difference really is the structure of the acid. And the structure is going to make it either easier or harder to donate H plus to solution. So some species of acids like this ClO4H or HClO4 down below, which is a strong acid, is going to have an easier time breaking this bond right here between the oxygen and the hydrogen, right? Because in order to donate an H plus, this bond will need to break. And there are a number of factors that are going to impact whether or not this bond between our conjugate base and the H plus, like how easy is it to break this bond? So the 3 variables that we're going to be discussing in the up and coming slides. First is bond enthalpy. This is the energy of the bond to H plus, right? So if, let's say I just use variable X to represent the bulk of the entire molecule, there's a bond that goes to this H plus, where the bulk of the molecule should have some kind of counter charge to it. So like for instance, H plus and Cl minus, or H plus and ClO4 minus. This bond right here between the counter ion and the H plus is going to have a particular strength. The higher the strength, the more difficult it's going to be to break the bond and dissociate your H plus. So we'll be talking about each of these things again in more details in the up and coming slides. Next up, we have electronegativity and resonance. These two things structurally kind of work together, where electronegativity, again, is just a brief definition, is like how, I should say easily, a negative charge can be stabilized by a particular element. So again, like fluorine, for instance, is very electronegative because it can very easily stabilize a negative charge. Whereas something like lithium is not electronegative because it is not able to stabilize a negative charge. And resonance is going to work with this because resonance is like the delocation of your electrons. How spread out can your electrons be? If we're thinking back to Lewis structures, we have learned of some Lewis structures where like double bonds or triple bonds can move throughout the structure. We are going to refer to this then, this resonance, or be considering it in terms of how mobile the electrons are in the structure. So we're not redefining resonance and we're not redefining electronegativity. We're just focusing on particular aspects of those definitions. All right, so let's look at bond enthalpy first, and then electronegativity and resonance to get an idea for how these variables are going to impact the strength of our acids. Okay, so we can predict acid strength in 2 different ways. We're first going to be looking at what we call the hydrohalic acids, but this is going to be an example of our non-oxo acid case. And oxo acids are going to be acids that have some type of polyatomic ion with oxygen in them, and we'll see how the arguments are going to differ between the non-oxo acid and the oxo acid in a second. So we're going to look at the hydrohalic acids as an example, or an acid that is comprised of H, this is being the hydro piece, and X is the halic piece, or the halogen here. And what we are able to see experimentally is that as we vary the halogen from fluorine down to iodine, down the periodic table, right, fluorine, chlorine, bromine, iodine, we see that the bond strength between the hydrogen and the anion, whatever the halogen is, decreases, right? So the enthalpy, the bond enthalpy between hydrogen and fluorine is very high versus the bond enthalpy between hydrogen and iodine, conversely, is very low. And we see that there is a steady decrease from fluorine to iodine down this table. So what this tells us about the acidic nature of the molecule is the greater the bond enthalpy we have, so like the HF case, the stronger the bond between the H and the F. What the strong bond between the H and the F means is that the hydrogen is not going to separate easily. It can separate if we put in enough energy, this much energy. We can break the bond if we put in 562.8 kilojoules for every mole of HF we have, but the higher bond enthalpy relative to some other molecules we're looking at, like the HI, means that the acidity of the molecule is going to go down. In other words, HF is a weaker acid. HI is a stronger acid. And we would be able to predict this just by the nature of the partial charge on our fluorine versus our iodine, right? Fluorine is a very electronegative molecule, or electronegative element in the molecule. It's going to be pulling a lot of electron density towards it, which is going to give it a very, very distinct negative charge. It's going to be very partially negative. And this negative is going to be able to hold the H plus more tightly. Not only that, but because the atom itself is smaller, these two atoms are of a more similar size, which means the electrons are going to be more evenly shared across this shorter distance, right? We have a short distance here, short bonding distance, and as we talked back in chapter 6, when we were talking about Lewis structures, the shorter your bonding distance, the stronger the bond. All right, so we have a very strong negative charge on our fluorine. We also have a short bonding distance here. Both of these factors are going to cause the strength between the H and the F to increase, giving us a weaker acid. The hydrogen is going to be less likely to change or separate. The hydrogen iodide, as a contrast to this, we have a hydrogen that still in solution would give us a plus charge. This iodine would still have a minus charge. However, this iodine is super big compared to the H plus. This means that the minus charge is going to be very spread out at a very large distance. If this is our nucleus and this is kind of the size relative to the nucleus of our atom, this very large distance here means that we're going to have a very large bond distance, and we are going to have a weaker bond between the HI as a result. In other words, the distance from this H plus to the iodine nucleus is so great that the hydrogen, this H plus, can just leave, and the iodine would not even notice the difference. Okay, so this is how we can describe the hydrohalic acid strength. And this approach, these arguments can be made for other types of non-oxo acids. If we have hydrogen directly bound to some type of atom, like H2S versus H2O, and we were going to predict which one of these two would be the greater acid, we're going to look at the size of the anion here and its partial charge to let us know whether or not the hydrogen is going to be more greatly held or more weakly held. And in this example, we would expect H2S to be the stronger acid. Since the sulfur is going to be bigger, its partially negative charge is going to be more spread out. This very large nature, this very large bond distance is going to weaken the bond between the H's and the S, hence the H being able to leave more easily. Okay, so let's compare this to oxo acid strength. An oxoacid is some type of acid. We have an H out in front, but this H is bound to something like a polyatomic ion, sulfate, for example, where we have oxygens present inside of the polyatomic ion. Oxygens present. Now, the nature of the oxygens being here is what causes the nature of this type of acid to differ from the previous, hence why we call them oxoacids. The oxygen is going to matter here. In the table to the right, we have an example of 4 different acids, and the only difference between them, structurally and formulaically, is an addition of oxygen. So our first is HClO, or the hypochlorous acid. Next is HClO2, which is chlorous acid. Next we have HClO3, which is chloric acid. And last we have HClO4, which is perchloric acid. So the additional oxygen going from top down, we can see is going to have a structural effect first on what the acid's going to look like. So here we have in our first, the hypochlorous acid, we have an H, we have an O, and we have a Cl. So this is kind of our color coding. The white is the hydrogen, red is an oxygen, and green is a chlorine. And as we change then the structure going down, we can see that we are placing more and more oxygens on our chlorine. So here we have 2 oxygens on our chlorine, next we have 3 oxygens on our chlorine, and last but not least, we have 4 oxygens on our chlorine. Now what this is going to do is increase the electronegativity away from the OH bond here. So in contrast to what we talked about before, in the hydrohalic acid case, like HF, I said fluorine was more electronegative. This is an electronegativity difference directly between the hydrogen and the species that's bound to it. Here we're looking at a greater electronegativity across the whole molecule. And the electronegativity now across the molecule is going to behave differently than the electronegativity difference directly between the hydrogen and the atom it is bound to. The difference it's going to play is the more oxygens we have present, as we can see here, separating the hydrogen from the oxygen to the chlorine, these blue arrows dictate that we are getting a greater electronegative pull away from this OH. That is going to be the acidic piece of the molecule, right? This OH, this OH, this OH, and this OH are where we have the acidic portion of the molecule. And the additional oxygens on the opposite side or further away from this acidic piece means that we are pulling electron density away from that bond, right? We're not just pulling electron density from the hydrogen to the oxygen directly, we are pulling the electron density all the way across to the other side of the molecule. What this means, or what it's going to result in, is that we're going to have less electron density directly between whatever our X is. In this case, it's going to be our oxygen and our hydrogen, right? We're pulling electron density away from the acidic piece of the molecule, totally away to the other side. This is going to, as a result, weaken the OH bond. If more electron density is being pulled away from the OH bond, there is less electron density to circulate between the hydrogen and the oxygen. The electrons that would be holding these 2 atoms together is now circling away, further away, spending less and less time between the O and the H as we increase the number of oxygens. This is going to result finally in a greater acidity. The perchloric acid, our HClO4, is going to be the strongest acid of all of the molecules that we have illustrated here because we have the greatest pull of electron density away from the hydrogen and the oxygen. All of the electron density being stripped away to the other side of the molecule is going to increase the acidity because we are decreasing the bond between the hydrogen and the oxygen here. The hydrogen is going to very easily drift away in the perchloric acid case. The rest of the table, we have some additional information. The oxidation number of our chlorine we can see is increasing. The chlorine is becoming more and more positive. Again, as we are increasing the electron density, pulling the electrons away from the chlorine. This last column here, we have this new concept known as Ka. The equilibrium constant here is going to give us a representation of the strength of our acid. How strong is it? We can see that in the first two cases, our Kas are pretty small. We have some number times 10 to the negative 8, and then some number times 10 to the negative 2. And as we increase the acidic strength going up to the chloric and the perchloric, basically what happens here is that we have reached a point where the dissociation between the H plus and the oxygen in the rest of the molecule is so large that we have effectively broken equilibrium. We are no longer looking at reversible reactions. In the lower two cases, we are looking at total dissociation. Chloric and perchloric acids are both strong acids. And because of this, there's no need for any type of reversible reaction representation. There's no need for any type of equilibrium constant. Anytime we're working with strong acids or strong bases, we are going to be able to use our good old stoichiometry to figure out what our limiting reactant is, what our theoretical yield is going to be, and what our excess reactant is going to be. All right, now that we've been spending some time going over the qualitative strengths of our acids, and well, we'll be talking about bases in a little bit, but our acids, let's look then at connecting our equilibrium constant expression with measuring the relative strength of a hypothetical acid. A 5.9 times 10 to the negative third molar monoprotic acid, monoprotic meaning that there is only one H plus, and the structure that we can see generically is here, so it's a little Ha molecule. It is dissolved in water and allowed to reach equilibrium with that water. The pH is then found to be 5.63. What's the equilibrium constant for this reaction? Now, this type of problem, fundamentally, we will be setting up very similarly to the problem that when we solved for the Kw, the equilibrium constant for water, we used the pH to find equilibrium concentrations. We're going to do the same thing here. The only difference is that we also have an initial concentration that is presented to us. We have to include the reactant in our equilibrium expression, so that's going to add 1 degree of difficulty, but not too much more difficulty. Right, so just like with any of our previous equilibrium expressions, we're going to set up what our reversible reaction is. So we have HA, this is aqueous, it is in water, which is a liquid, reacting reversibly to give us A minus aqueous and H3O plus aqueous. We can set up our ice table, equilibrium change, or initial change in equilibrium. Initially, we are told that there is a 5.9 times 10 to the negative third molar monoprotic acid that is dissolved in water. Before it reaches equilibrium, this is the concentration, the 5.9 times 10 to the negative 3. So we are going to have to really be reading into these problems to figure out where exactly in this table does the information go. Since we are told this is the concentration before equilibrium is reached, we will assume that this is an initial condition. Water, just like before, it's a liquid. We are looking at a heterogeneous equilibria. We don't have to include the water. The concentration of our A minus and our H3O plus, initially we are not told any information. We are only told that we are adding HA into water, and that is reaching equilibrium, meaning that we do not have any A minus or H3O plus initially present. This information we can use to tell us which direction the reaction has to shift in order to reach equilibrium. We are going to see a dissociation of reactants into products, meaning that we are going to shift away from the monoprotic acid and in order to create some of our product here. At equilibrium, then, we would expect to see 5.9 times 10 to the third, or 10 to the negative third minus x for a concentration, as well as x and x for both of our products. From here, we are now supposed to find what our equilibrium constant Ka is equal to. Let's write this over here. Ka, which is equal to the concentration of A minus times H3O plus, all divided by concentration of HA. This expression was on the previous slide, but you would also be able to write it for whatever your reversible reaction is, assuming you know what your weak acid is and you know what species it dissolves into. Again, we're always looking at product divided by reactant concentrations. We know that our reactant concentration is going to be lost a little bit. We're going to generate some product. This is going to give us x squared all divided by 5.9 times 10 to the negative 3 minus x. But here we can see that we have no known Ka. We don't know initially what our x's are equal to, so it's like, how do we solve for K? Well, just like with that previous problem, when we solved for Kw, we used the pH, we can do that here. The pH tells us the concentration of H3O plus when we are at equilibrium, right? The pH is then found. Then meaning after equilibrium has been reached. So we can solve for the H3O plus concentration since this is going to be equal to 10 to the negative pH. The H3O plus concentration then will be equal to 10 to the negative 5.63, which is equal to 2.34 times 10 to the negative 6 molar. This is going to be what our x value is equal to, right? Since at equilibrium, the concentration for H3O plus is x, and the, in the table, and we just also found for what that concentration is, meaning that this is our x. Not just in the H3O case, or H3O plus case, but also the A minus, and also the amount that is going to be lost from the reactant, right? Again, x is x is x. It's all the same x. So we can use this concentration now in the numerator and in the denominator of our equilibrium expression for our weak acid in order to find what the Ka numerically is equal to. This is going to be a 2.34 times 10 to the negative 6 molar squared, all divided by 5.9 times 10 to the negative 3 minus 2.34 times 10 to the negative 6. All right, and what this is going to be equal to then is a 9.28 times 10 to the negative 10 unitless value, right? In our balance of product to reactant, this very small Ka tells us that we have a lot of reactant still left and not a lot of respective product. This is what defines our acid, in this case, again, as being a weak acid. We do not have a complete dissociation. In fact, we have a very small dissociation. But this dissociation is not so small that it's incredibly insignificant, right? We still saw a pH change from the neutral pH of water. We saw this change down to a pH of 5.63. So even though we have a very small dissociation, this dissociation is not completely negligible. We can't just ignore it altogether since we have fundamentally changed the nature of the beaker of alleged water sitting in front of us. So the weak acids and weak bases that we're about to also showcase, we are going to have to be working with these types of calculations from the ice perspective. All right, so as we move into weak bases, we can also calculate percent dissociation for weak bases. Similarly, we're going to be comparing the amount of product at equilibrium divided by the amount of reactant initially. So that concept, or that setup for the equation is going to be the exact same. So what is a weak base and how can we talk about it similarly or in parallel to the weak acid cases? Well, a weak base is something that's going to also react with water reversibly, but now we are going to cause some type of OH minus to come about. Our base in the generic notation is going to be represented by this B for base. It will interact with water reversibly, water again being a liquid here. Everything else is aqueous because everything else is dissolved inside of the water. Now the base is going to pull one of the H pluses to it, and that will result in an HB plus. This plus sign results from the H that the base pulled to it having a positive characteristic to it. This is also going to leave OH minus behind. The KB is, again, another form of an equilibrium constant. This is another type of Kc. A Kc, when it comes to weak bases, we notate with this lowercase b here, meaning a weak base is what we are looking at. But the setup to find this is, again, the exact same as every other equilibrium constant that we've found so far. We're looking at a ratio of products divided by reactant. The products here are the Hb plus and the OH minus, and the reactant we started with was the weak base itself, B. So I know we have so many different Ks now. We have KC, we have KP, we have KSP, we have KA, we have KB. Where does it end? There are so many Ks. The important thing to remember, the underlying thread that connects every one of these Ks, is that all of them are equilibrium constants. They are all set up in the exact same way. So if you have a reversible reaction, you're going to be taking product divided by reactant of anything that is in the aqueous or gaseous phase. That is it. So even though we keep introducing these new contexts for using equilibrium constants and we have more subscripts, just remember that the subscript, its purpose is just to give you more information about the reaction you are working with. In this case, if you were to pull up a KB because you have written an expression that matches an equilibrium constant, you thought it was just a pure Kc and you find out it's a Kb, you're like, oh, you're right, this equation is basic. I am working with a weak base. That's all the subscript is meant to do, is to give you more information about the problem. So please try not to get too thrown off by it. It's always products divided by reactants. All right, so similarly, now that we have our Kb, the equilibrium constant pertaining to weak bases, defined, as well as the reversibility of basic reactions or dissociations defined, let's ask ourselves a very similar question to what we did earlier in the lecture. What makes a base strong? Well, a strong base is defined very similarly to that of a strong acid. Strong bases are those that are stronger than or equal to the conjugate base of our solvent OH-. So a strong base is going to be a base that completely donates OH- through the ionic dissociation of like the ionic crystal itself. So for instance, if we're considering sodium hydroxide, this ionic compound, which you can actually see pictured down below, these are little solid chunks of sodium hydroxide. These completely break down into sodium plus and OH-. This is not a reversible reaction. This is a complete dissociation, which means for every 1 part sodium hydroxide we dissolve in solution, we are going to get 1 part of hydroxide being present in solution. And as we know, hydroxide is the conjugate base of our solvent, which is water. So any of those 8 strong bases from our previous list, so the 8 compounds, just as a general reminder, the lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, barium hydroxide, and strontium hydroxide. If I got all of these in the same order as the table as before, that's awesome. If some of them are flipped around, it's fine. The point is that each of these 8 bases, each of these 8 compounds will completely dissolve in solution, meaning that we are getting a complete dissociation of OH- per every 1 mole of these strong bases that are being dissolved in water. Now, other bases are not going to have a complete dissociation. So other bases, even something like, let's say hypothetically, beryllium hydroxide, are not going to completely break down in water due to their solubility. Oops, hold on. All right, erase my mistake. As I was saying, these things are not going to be able to completely break down inside of solution, this beryllium hydroxide, because beryllium 2+ is not actually that stable of an ion in water. It is going to want to recombine with this OH-, giving us a reversible solubility. And as we've already talked about KSP, if your solubility is reversible, that means that you're not going to get complete dissociation of your ions, meaning in this case, we don't get complete dissociation of OH-. That is what makes something like beryllium hydroxide a weak base, whereas all of these other hydroxides count as strong bases. All right, well, we're going to ask ourselves, again, a very similar question as to what we did with the acidic case. What of the structure of these bases makes it easier to accept H+? Right, so it's not just about having OH- in solution. A base ultimately acts as a base because it is accepting H+ from solution, or H+ from another acid around it. So What I will acknowledge are these variables, and I will also acknowledge that they function very similarly to they function very similarly to how we discuss them in the context of acids, just kind of in reverse. So for instance, electronegativity and resonance. We've already seen how these variables played into the ease of donating an H+. Well, if we think about something like, let's say, F-, this is a very small ion, negative charge, very easy at stabilizing a negative charge, meaning that it's going to also be able to pull an H+ towards it because this negative charge on the ion is very small and concentrated. Now, we wouldn't consider F- to be a strong base, but it is going to be a stronger weak base, if that makes sense. So on that scale of strong to weak, it will be a little bit closer to the strong side, even though it's not completely strong. All right, there are some other variables, though, that play into how strong a base can be. And these variables you'll see more of in organic chemistry and future higher level chemistry courses. Namely, of all of the other variables that we could address, I'm going to focus on sterics. It is the variable that's at least, let's say, the most unique of the other variables that I could discuss for how we can consider basic strength. Sterics pertains to the shape of the molecule itself. The shape of the molecule. So for example, if we are working with a structure where the partially negative location of the, on the molecule, the section that will actually act as a base, if it is blocked by other sections of the molecule, for example, let's say something like this nitrogen, which nitrogens with their two lone pairs, it's very easy for them to act as Bronsted-Lowry bases. If this nitrogen with its partially negative charge was actually blocked by another section of the molecule, let's say hypothetically there's a carbon with a couple of hydrogens off of it, like so, this nitrogen is going to be a little bit more difficult to gain access to because of all of these hydrogens that are bonded off of our carbon right next door to the nitrogen. So the shape of the molecule is going to play into how strong a base or even an acid could be. Namely, though, the base, because if the acid can't actually connect with this location of the base, then we're not going to see any H+ exchange. There's no incentive for the H+ to be donated to the base if the base can't actually accept it. So again, you'll learn more about the impact of things like sterics, other variables like sterics, in future classes in our chemistry major. So let's look at how the setup for this problem, when we're working with a weak base, like yes, now we're working with a Kb, but we're still setting up this type of problem in the exact same way as every other type of equilibrium problem that we have worked with so far. The only additional pieces are that we are now told that we are working with a weak base, and we are ultimately trying to find a pH. What is the pH of a 0.85 molar aqueous methylamine solution, where methylamine is CH3NH2. We are also told what its Kb is equal to here. Okay, so how we start this problem. We are not given any type of reversible reaction. So dating back to last semester, chapter 8, when we started writing reactions, that's going to be the first thing we have to do. We're working with some type of equilibrium, some type of weak base. We need to know what the reaction is before we write any type of equilibrium expression. So we're told we have a base here. It is explicitly not said in the problem that it's a base, but again, we are told that we have a Kb. This Kb lets us know that the CH3NH2 is a base. So even if you didn't have this header up here, right, the pH of a weak base, if that wasn't there, if it was just the wording presented as it is, you would still be able to identify that the CH3NH2 is a weak base because you're working with a Kb. So that's the usefulness of these subscripts. The CH3NH2 aqueous, as it interacts with water, and we are told that we are working with an aqueous solution, so we know that water as a liquid is going to be present. These two things will react following the structure of the generic formula previously given, that one of these hydrogens is going to move to our base giving us CH3NH3. The base now will have a plus sign associated with it since it has taken an H plus onto itself. This will be aqueous, and the remainder of the water as this hydrogen moves over is going to be an OH minus. And this will also be aqueous. So yes, we were not given an equation, but we have the logic and tools now to write out whatever this generic equation is going to be, whether or not we're working with a base like here or an acid. So as the H plus has moved over, we now have a reversible reaction. We have some type of Kb, and we are asked to find what the pH for this solution is going to be. Now, in order to find pH, let's kind of backtrack. We need to know concentration of H plus at equilibrium. That is the important piece. pH, again, is always measured at equilibrium unless explicitly stated otherwise. So we are going to be needing to find an H plus at equilibrium here. Well, since we're not working with an acid and we don't have an H plus given in our generic equation, right, there is no H plus here, we're going to end up needing to find concentration of OH minus to find concentration of H plus to find the pH. So we have plenty of steps inside of this problem and a number of equations and tools at our disposal to solve it. So the first thing we're going to have to solve for, to set up and solve for, is the equilibrium concentration of OH minus. This is something that we know how to do since we have a reversible reaction and we have the ICE table format at our disposal. We are told what the initial concentration of our solution is, 0.85 molar CH3NH2 before any type of dissociation happens. Water, don't care about it. We don't have any of our product initially present. The reactant still needs to dissociate. We have only just added this 0.85 molar concentration of our reactant into solution. It needs to shift from reactant to product. This reaction needs to shift in order to create some of this product now. We would use this to be able to predict that we're going to be shifting from reactant to product and use this information 0.85 minus x, x, and x in order to find what the concentration is going to be equal to. Now we can see that we are not asked for all of the equilibrium concentrations here. Ultimately, we're trying to find a pH, which means we have to find concentration of H+, which means we have to find concentration of OH-, which is exactly equal to our value of x. In other words, once we find x, we can start this immediate thread on our way to find the pH of our solution. All right, so let's set up to solve for our x. We have our equilibrium expression that we can set up since we have a Kb. Kb is going to be equal to the concentration of our CH3NH3+, all times the concentration of our OH-, all divided by the concentration of the CH3NH2. All right, and as we then start inserting some values into this equilibrium expression, the CH3NH3+ as well as the OH- is equal to x. Kb is equal to x squared in the numerator. And what I'm going to do here is take one of our shortcuts. So the initial concentration of our reactant is over 1,000 times greater than what the equilibrium constant is equal to. What this means is that I'm going to effectively drop this minus x here. I'm only going to include the 0.85 present down below. All right, so I'm taking a shortcut here, though, and I'm being explicitly clear about taking a shortcut. And all of this now is going to be equal to our Kb, which is equal to 4.4 times 10 to the negative 4. Now, to rearrange and solve for x, x being the thing that we care about here, at least initially, our x is going to be equal to a 0.0193 molar. So this is equal to our concentration of our OH- at equilibrium. This we can use to find what the concentration of H+ is equal to. How can we do this? Since we are working in an aqueous solution, if we have some OH- present, we have to have some H+ present because of the nature of H2O, breaking down reversibly into H plus and OH minus. And since our solvent is water, this is happening all around the solute. The balance of the H plus and the OH minus concentration is dictated by our Kw, which is equal to H plus times OH minus. Now we know what the OH minus concentration is. It's the 0.0193 molar. So let's insert that up here, 0.0193. Our H plus is what we don't know, and so we're going to have to solve for that using our Kw, which is equal to 10 to the negative 14. All right, so what this means is when we rearrange and solve for our H plus, we are going to find a value that is equal to 5.18 times 10 to the negative 13 molar. I'm sorry that my math is now kind of like circling everywhere on the slide. This is the value we can use now to insert and solve for our pH. Since pH is equal to the negative log of the concentration of H plus, our pH are going to be equal to the negative log of the 5.18 times 10 to the negative 13, which is going to be equal to 12.29. This pH is greater than a pH of 7, which would imply a basic solution, and that is exactly what we would expect since we are working with calculating the pH of a weak base in solution. So all of this is coming full circle. Now, had you gone about solving for the pH in a slightly different way, after solving for the OH minus concentration, if you went the route of finding the POH and using that to solve for the pH, you could definitely have done that. You would have ended up with the same answer, a 12.29 being the measured pH of your weak base. And with that, I think it's time that we call it a lecture. So today we did focus on acid-base strength. There are plenty of metrics for determining strength. So either we're going to be looking at the actual structure of the acid or the base to determine relatively how strong it could be. If we don't actually have any specific numbers to put to our problem, we can even just compare structurally based off of things like electronegativity and resonance to predict how relatively strong one of these acids or bases could be. We could also just observe our table of strong acids and bases and say like, yes, I identify that this acid is in fact a strong acid, which means this other acid is gonna have to be weaker than it. But we also learned today using our equilibrium constant metrics like our Ka and our Kb, we can also calculate exactly how strong our acid and base are, not just in terms of Ka and Kb, but also then in terms of pH and POH. All right, so I would definitely recommend you get some practice in with these section review problems. As always, if you have any questions, please do not hesitate to reach out and ask me those questions. In addition, do your homework if you have some homework, and until next time, class is dismissed.